Okay, now in the previous videos, I discussed the fact that radiation can exist as a waveform, but it also can exist as a stream of particles. And if you remember, we said that these particles are called photons. So, based on this fact, this guy, whose name I'm quite sure I'll be mispronouncing, DeBrogle, I think he's from France, he considered the possibility that maybe matter, anything material, material objects, even small as particles, behave as objects, as I just said before, but also take on wave-like behavior when they're moving. So he did some theoretical work and he came up with this equation. And this equation basically helps you to calculate the wavelength of a moving object, right? Lambda is a wavelength, as we said before. H is Planck's constant, as we said before. And m is the mass of the object. And the volume, V is the velocity. And in terms of the units, lambda would be in meters. The unit of H would be joules second. The unit of mass would be in kilograms. And the unit of velocity would be meters per second. All right, so those are the units that have to be in place in order for this equation to work accurately to determine the wavelength of any object whatsoever. All right, so this is again another example of how purely scientific theoretical work would lead to something of a technological value, because in the case of de Broglie, his calculation led to the development of the electron microscope, which, if you don't know, is the most powerful microscope ever, several times more powerful than the normal optical microscope. Okay, so let's talk about another development. Werner Heisenberg, he came up with what is known as the uncertainty principle, and it talks about the fact that we simply cannot know simultaneously exactly where a small particle, such as an electron or a proton or even an atom, is and how exactly it is moving. And there's a mathematical equation which describes it, which we won't get into in this lecture. But basically, what Heisenberg is talking about is the fact that you don't know, there's no way of knowing where a particle is and exactly its speed, basically, or how it's traveling, what direction it's traveling. And the reason for that, his reasoning behind it, is that the act of measuring the particle actually interferes with the particle. So basically what they're saying is that if you could develop some means of determining where a particle is at a particular instant, the instant that you determine where the particle is, it won't be at that point anymore, because basically whatever efforts you made in order to measure or determine where the particle is would basically displace that particle, and therefore what you would have seen at the instant is where the particle was. So just to give you a pictorial demonstration of that is what that shows in terms of the uncertainty principle. So let's say you have a special microscope that can basically observe a particle such as an electron. And let's say it's an ordinary optical microscope. Now, because it's optical, it depends on light. And when it comes to small particles, it can be affected by the particles of light, the photons. So in order for the optical microscope to detect the object, the photon would have to reflect off the electron. We're using an electron as an example of a small particle in this case, and be directed toward the microscope, right? But what happens is that when the electron is hit by the photon, the electron is displaced. So therefore, by the time the photon reaches the microscope would have detected where the electron was previous to that, whereas the electron would be somewhere else. All right, so that's basically a representation of what Heisenberg's uncertainty principle is all about. Now, this is important because this affects the Bohr model, because the Bohr model seems to suggest that there's some certainty in terms of where the electron would be, because if you remember in the Bohr model, specifically to hydrogen, the electron would be basically within well-defined orbits. Well, the uncertainty principle basically um, contradicts that basically. So the Bohr model, even though it works well, especially for one electron atoms, it is not accurate in terms of giving us a true picture as to how the electrons are arranged in the atom. So the Bohr model is not accepted as the model that accurately represents the atom. Okay, now in order for us to understand how we arrive at the current understanding of the nature of the atom, especially in terms of how the electrons are arranged in it, I need to talk to you about wave functions. Now, let me just warn you that this is very abstract, and unfortunately, we won't be able to get into all the details of this concept because this concept is a very important concept known as quantum mechanics. You may encounter this in your physics courses if you have to do physics, or if you do higher level chemistry courses. Physical chemistry 1, in most cases, is where you would encounter this particular topic in more detail. So what we'll be going through basically is really the surface of the whole concept of quantum mechanics. And this is basically a different approach from the normal Newtonian mechanics, which basically assumes that objects obey the laws of motion according to Newton. Quantum mechanics basically treats small particles in a different way because of the wave-like properties that are displayed by these particles when they're moving. For example, electrons. All right. So this guy is a guy who developed wave mechanics, the concept of wave mechanics, to describe the hydrogen atom, and and then it was extrapolated to other atoms and molecules and other systems as well. Now, the key thing for wave mechanics or quantum mechanics is the existence of what is known as a wave function, right? Which is basically a solution to an equation that was developed by Schrodinger. So we have the Schrodinger equation, which I won't even show you what it is. You can look it up if you're so interested. You have the Schrodinger equation, and the solution to that equation is called the wave function. And that wave function is basically a representation of the energy state of an atom. Now, how do we interpret the wave function? Because the wave function is also another equation. Well, the wave function basically, if it's squared, gives the probability of finding an electron in a small volume of space around the atom. All right? And that small volume of space around the atom, we call that an orbital. So let me just put here, let me take my pen, and so that small volume is called an orbital. All right. So basically, the orbital of an electron is the region in space where the probability of finding an electron is very high, above 95%. All right. So in our modern understanding of the nature of an atom, we don't refer to orbitals, or we don't refer to orbits, I should say, when it comes to where the electrons are located, because that's the Bohr model idea. And as we said before, we don't go with that idea anymore in light of the Heisenberg uncertainty principle, among other reasons. So instead, we talk about an orbital. All right. So basically, the picture that is developed concerning how the electrons are arranged is that the electrons are arranged in regions, which are known as orbitals. And sometimes you hear terms or read of terms referring to orbitals, which talks about an electron cloud. Basically, again, indicating that we cannot pinpoint where an electron is at a particular instant, as predicted by Heisenberg. But basically, we can talk about a region in space where there's a probability of finding an electron. All right, so that's what we call the orbitals. Now, the solution to the Schrodinger equation, as I said before, are the wave functions. And for the solutions to work, the hydrogen atom must have three parameters that have specific integers, which are called quantum numbers. And a wave function with a set of these three quantum numbers, we call that also an orbital. So this is just another definition of an orbital. It's a wave function which has the three sets of quantum numbers that would be unique to it, all right? These orbitals allow us to visualize the region in space where there's a probability of finding the electron, which again is the orbital. Okay, so we're going to deal with each of these quantum numbers in turn. The first of which is called the principal quantum number n, and this n is basically the same as the n that you would encounter in the Bohr model. All right, n is basically a positive integer starting from 1, right? So n would be equal to 1, or can be equal to 2, equal to 3, all the way to infinity, right? So the relationship between n and the orbital that is within it is that the size of the orbital and its energy is dependent on n, right? So basically what we're saying here is that as n gets larger, then the energy of the electron in that orbital increases, and the size of the orbital also increases, right? Another statement here is that orbitals with the same n value are said to be in the same principal shell or principal energy level. So you'll see these two terms, shell or energy level, used interchangeably in this discussion, all right? Basically, all the electrons, or all the orbitals, I should say, that have the same n value are said to belong to the same principal shell, all right? Then we have what is known as the angular momentum number. In some textbooks, they call it the azimuthal quantum number, L. And this value, the value of L, are integers as well, and they can go from, hold on, let me see here. Let me go back to, right, so the L values can start from 0 and go again all the way up to infinity, right? We only show you the first 4 here because that would be our concern at the moment. Now, there are some letters that are associated with these numbers, right? S would be for 0, P is designated for 1, D for 2, F for 3, and then after that, it goes in an alphabetical order, G, H, I, etc. Now, what information can we get from these values? Well, these values give you some information about the shape of the orbital that are within, that are assigned these numbers, all right? So just to give an idea as to how you determine what are the correct L values for the correct N values, if the possible values of L can go from 0, which is a minimum, and all values in between to n to the -1, where n is the principal quantum number that we saw before. So for example, in the case of n equal 2, if n is equal to 2, then the values for L can only be 0 and 1, right? It cannot be 2 because 2 would be above the range, because since n is equal to 2, 2 minus 1, which is 1, would be the maximum value that L can have. Let me just give you some other examples. Let me keep this, and let me go to my white paper here, and let me kind of zoom in a little bit so as to get more space. Okay, so let's say if n is equal to 3, then the possible values of L, I'm sorry, is equal to 2, 3, I'm sorry, is equal to 2, 1, 0. If n is equal to 4, then the possible values of L would be 3, 2, 1, 0, 0, and so on and so forth. If n is equal to 5, then L would be equal to 5, then n will be equal to 4, 3, 2, 1, 0, and so on and so forth, right? So basically, we can conclude that the n equal 3 energy level will have three, what we call sublevels. And the sublevels will be represented by the numbers, or we can use the letters I told you before. So remember, S would be for L equal 0, P would be for L equal 1, and D would be for L equal 2. All right? In the case of the N equals for energy level, then the sublevels or subshells, let me write down the word subshells here. So subshells, sublevels, same thing, right? So as far as the subshells are concerned, within the N equal 4 shell, these are the L values, and the corresponding letters designated for each of these subshells would be S for 0, P for 1, D for 2, and F for 3, and so on and so forth. All right? Okay, so let me get back to the, get out of this here. Let me get back to the PowerPoint. Okay, so go back to the big screen. Okay, so as I said before, the types of orbitals have different shapes. So S orbitals have a particular shape, P orbitals have a particular shape, and so on and so forth. We're going to get into the shapes later on, so you have a picture of what we're talking about. And as I said before, all orbitals having the same N value and the same value of L are said to be in the same subshell. So within each particular energy level, where you have subshells existing, or different subshells that existing, then those subshells basically will have the same shape. Okay. The third quantum number is called the magnetic quantum number, symbolized by the letter ML, or M sub L. And this gives you information about the orientation in space of the different orbitals. So what you'll find is that the values, the possible values of L is dependent on, I'm sorry, let me repeat that. The possible values of ML is dependent on those of L. So if L is equal to 2, well, let me just give this general statement right here. Let me go to my pen. So just to highlight here, right here, the possible values of ML can range from minus L to plus L, all right? So in the case of L equals 2, then the possible values of ML would be all digits from minus L, which is minus 2, minus 1, 0, 1, and then to plus 2, right? So let me go to my white paper here again. So let me draw a line here to make a distinction between what is above and what's below. So down here, if L is equal to 3, then the possible values of ML would be plus 3, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. All right? If L is equal to 4, then the possible values of ML would be plus 4, plus 5, plus 3, I'm sorry, plus 2, plus 1, 0, minus 1, minus 2, minus 3, minus 4, and so on and so forth, right? So what this tells us is that within each sublevel, you have orbitals, each of them having a separate ML value. In fact, let me go back to the PowerPoint here. Hold on 1 minute. Okay, so basically, and that's because each orbital has their own specific directional property, because remember this says here that the ML value determines the orientation in space of the orbital. So basically what this is saying is that within the L equals 2 sublevel, there are 5 separate orbitals with their own directional properties, right? Each orbital is designated an ML value, all right? So basically, if you know the N value for a particular shell, you can determine how many subshells are present. And if you know the L value for a particular subshell, you can determine how many orbitals are present within that subshell. All right. In fact, this table here basically summarizes the relationship between n, ml, the number of subshells, and the number of orbitals within the subshell. So in the case of the first shell, which is n equal 1, which is the lowest energy shell, there's only one L value that can be calculated based on the rules that we just covered, and that is L is equal to 0. And if L is equal to 0, that means that ML is equal to 0. So what that tells us is that within this subshell here, there's only one orbital, right? Now, the designation of that orbital is 1s, right? 1 is the n value, which we got from here, and s is the type of subshell, which is basically as a result of L is equal to 0 here. And there's only one type of subshell present with orbital within that subshell, and that is the one where ML is equal to 0, all right? Now, in the case of the second shell, right, the n value is 2, right? Now, of course, for n equal 2, there are two possible values of L. That would be 0 and 1. If L is equal to 0, then there's only one possible value of ML. So therefore, there's only one type of orbital that is present within the first subshell of the second shell, and therefore we designated 2s, right? However, in the case of this second shell, we have a situation where L can also be equal to 1. Now, in the case of L equal 1, there are three possible values of ML, -1, 0, +1, right? And therefore, what this indicates is that there are three orbitals within the L equal 1 subshell. So that's why we have three orbitals here in that subshell. And therefore, the designation would be 2p for each of them, 2 for the shell that they're from, and p for the subshell that they're from, where L is equal to 1, and there are three of them, right? And you can basically follow the same logical argument to explain this side of the table here, representing the third shell, the fact that as a result of looking at the L values and ML values that are possible, you can come to the conclusion that there are three sublevels, right? Three subshells designated 3S, 3P, and 3D, and these are their numbers. In fact, basically we can come up with a rule of thumb, so to speak, concerning how many sublevels are present within each energy level, principal shell, whatever term you want to use. So if n is equal to 1, then there are three, there's one sublevel. Maybe I should do this in the form of a table. So n value, or let me just put n. Let me put number of shells, number of subshells. Let me leave it at that, all right? So if you have n equals 1, the number of subshells would be 1. If you have n equals 2, the number of subshells would be 3. When n is equal to 4, the number of subshells, 3. The number of subshells would be 5. When n is equal to 4, the number of subshells would be 7. All right, so I'm just going to stop there. We could go on, but again, for our purposes, we're only concerned with up to the 4th shell. We could actually go on, because if n is equal to 5, then the number of subshells would be 9, and so on and so forth. Okay, so that's the relationship between the n value and the number of subshells, all right? Okay, so just to give you a three-dimensional picture of what we're talking about here in terms of the different types of orbitals. Electrons, of course, are negatively charged, and therefore they're going to be attracted to the nucleus, which are positively charged, right? So therefore, what you'll find is that as you move away from the nucleus, the probability of finding an electron decreases. So this is basically the plot for the 1s orbital in the first shell that you see here. Psi squared is basically the wave function squared. Psi is usually the symbol, a Greek letter, the symbol that is used to represent the wave function. So as you see here, it decreases as the radius or the distance from the nucleus increases. Now, what is more useful is calculating the probability of finding an electron within a volume of sphere with a radius r. So instead of using psi squared plotted on the y-axis, we use this here, 4 pi r squared times psi squared, which gives you the probability of finding an electron within a volume of the sphere. And when you do that for the 1s orbital, you'll find that this is a plot right here. All right. Whoops. So you'll notice that there's a peak at this juncture right here, which basically represents the maximum volume of electrons that will be found within a sphere of radius r. All right. So that's important because of what we're going to see here. So basically, that gives you a picture of the three-dimensional shape of the 1s orbital, right? So these are the two previous plots I talked about here and here. And basically, if you were to plot that, you'll see that it looks something like this, right? And you'll notice most of the electrons would be located, as I said before, at the nucleus or near to the nucleus, and the probability decreases as you go away from the nucleus, right? But what this plot indicates is basically the probability of finding an electron within a particular volume, not just from the distance from the nucleus, but within a certain volume. So basically, it seems as if this here would represent that plot at the maximum point, right? So at the maximum point here, most of the electrons within the spherical volume here would be, most of the electron density, I should say, would be found within that spherical volume. Okay, now if you were to do a similar plot for the 2s orbitals, what you'll find is that in the case of plotting the wave function versus the distance from the nucleus, you'll find that this is a plot, and you'll notice that there are two regions here, where that value would be 0. And if you do a plot of the volume region versus the distance, you see that it goes up here to a maximum and then comes down here and then goes up to a maximum here. So what this indicates is that there's a region, circular region, which is what you see here when you plot it in a three-dimensional way, which is called the node, where the region of the probability of finding an electron in that region is 0. All right. And what you'll find is that as you go from the 1s to the 2s to the 3s, the number of nodes increases. So the 1s orbital has no nodes, the 2s orbital has 1 node, the 3s orbital has 3 nodes, and so on and so forth. Okay, now as far as the p orbitals are concerned, this is what they look like, right? The p orbitals, as you can see, each of them will have a dumbbell-shaped, they're dumbbell-shaped. And not only that, but they exist in 3 planes or axes that are mutual right angles to each other. So you have the px orbital, which is along the x-axis shown here. You have the py, and you have the pz, right? So this is what they look like individually, and then together, collectively, this is what they appear like, all right? So that's basically the p orbitals. And then we have the d orbitals, which comes in sets of 5s. So in this case here, I won't even expect you to know how to draw them or arrange them. As you can see, it's a bit more complex. But you do need to know that there are 5 of them. Where d orbitals exist, there are 5 d orbitals, all right? And that's basically what they look like separately, here, 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 and here. And collectively, this is what they look like, all right? And I won't even go into the f orbitals because that's even more complex. But you do need to know that there are 7 f orbitals, all right? Okay, so there's one more quantum number which we have not talked about, and that is known as the electron spin quantum number. And you're going to see the importance of this in the next chapter when we talk about electron configuration. Now, basically what this says, what this spin quantum number, the information that you can get from it, is basically the direction of spin of the electrons. Now, this involves some physics which you may or may not have encountered, but basically, if you have any charge that is moving, then it generates a magnetic field, right? So for example, one example I can remember from my days of doing physics, if you have an electric current moving through some wire, copper wire, then the motion of the electron will generate an electric field. And there are some calculations that you can perform in order to determine the magnitude and the direction of that field. Now, when it comes to small particles, charged particles like electrons, if they're spinning, then they generate an electric field. And what is shown here is the nature of the field that is generated by such particles. So here we have an electron that is spinning in this direction. Now, there's a rule called the right-hand rule, right? Which basically says that if you have your fingers of your right hand curled around and your thumb is pointing away from them, then the direction of your fingers will indicate the direction of spin of the electron, and the thumb will indicate the direction of the magnetic field. So based on that, we can predict that when the electron is spinning in this direction, the magnetic field generator will point in the direction shown here. And of course, if the electron is spinning in the opposite direction, then the magnetic field will be pointing in the opposite direction. So the spin quantum numbers have been designated, and there are only two possible spin quantum numbers because it was determined that the electrons can only spin in one of two directions. So for the electron spinning in one direction, the spin quantum number, which is ms, is equal to plus half, and then when spinning in the opposite direction, ms is equal to minus half. All right. So those are basically the two quantum numbers associated with the directional spin of electrons. All right. And these numbers are not in any way dependent on the n value, the L value, or the ML value, right? ms can only be equal to plus half or minus half. All right. And this is the experiment, which I won't go into in finer details to explain how the ms values are determined, but basically Stern and Gerlach came up with this experiment where they have a stream of silver atoms passing through a slit and then passing through a magnet, and it was determined that what will happen is that when the beam or the stream of silver atoms emerges from the magnet, they go in different directions as shown here. All right. Some are deflected up, some are deflected down. And they did their theoretical calculations, and they determined that that is due to the fact that the electrons in these atoms are spinning in opposite directions. And that's how we end up with the spin quantum numbers. Okay. So as stated here, the interaction of the electric spin with the magnetic field caused a splitting of the beam. All right. And as I said before, that led to the ms values. Okay, so that's basically it for this chapter. So the next chapter will be chapter 8, which delves into more information about how the electrons are arranged. All right. Okay, so that's it for now.